the night sky looks still. It is not. You are sitting on a planet spinning at over 1,000 kilometers per hour, orbiting a star at 30 kilometers per second, riding a galaxy that is itself falling at 600 kilometers per second through the universe. In this video, we will follow the layers of motion that hold the cosmos together, from the ground beneath you to the expansion of space itself. If the mysteries that reach us from space are the kind of thing you like to sit with, that is what this channel is for, and subscribing is the easiest way to let the next one find you. That is the only such request you will hear. Everything after this is the motion. The first of those numbers is easy to verify, and it has been known for a very long time. The Earth rotates once on its axis every 24 hours. At the equator, the circumference of the planet is about 40,000 kilometers, which means a point on the equator is traveling, just by virtue of the rotation, at about 1,670 kilometers per hour. At the latitude of New York or Madrid, the rotational speed is closer to 1,200 kilometers per hour. At the poles, it drops to nothing. Wherever you are right now, unless you happen to be at one of the poles, the ground beneath your feet is sweeping eastward at a speed greater than most commercial aircraft crews. You do not feel it. Nothing in your inner ear registers it. The reason is simple. You are moving with the ground. Your body, the air around you, the building you are sitting in, the trees outside the window, all of it is being carried along at the same speed in the same direction. There is no relative motion between you and your surroundings, and motion is something the human senses only detect through changes in relation to nearby things. A passenger on a smoothly cruising airplane does not feel the speed of the plane. They feel only the small disturbances of turbulence, the gentle bank of a turn, the slight push backward at takeoff. Once the plane is in steady flight, the sense of motion fades. The same is true of the Earth, only the steadiness is even better. There are no turns, no changes in speed, no turbulence. The rotation has been perfectly smooth on human timescales for the entire history of life on the planet. The second number is also easy to state. The Earth orbits the Sun once every 365.25 days, along a path about 940 million kilometers long. To complete one orbit in a year, the Earth travels at about 30 kilometers per second, which is to say 108,000 kilometers per hour. This is roughly 30 times faster than a rifle bullet. It is faster than the orbital speed of the International Space Station, and considerably faster than any human-made object has ever achieved except for the Parker Solar Probe at its closest approach to the Sun. Every minute of your life, the Earth covers about 1,800 kilometers along its orbit. By the time you have finished reading this sentence, you have moved about 600 kilometers further along the path the Earth traces around the Sun. You do not feel this either. The orbital speed of the Earth is, again, a speed shared by everything in your immediate vicinity. The atmosphere, the oceans, the satellites, the air molecules drifting through your room are all participating in the orbit. There is no resistance to it. There is no wind from the Earth's orbital motion, because empty space is empty and the orbit does not push against anything. The whole planet is, in effect, falling around the Sun continuously in a curved path held in place by the Sun's gravity, and falling produces no sensation of weight. The astronauts on the International Space Station are doing the same thing, only in a tighter orbit around the Earth, and they too feel weightless. The third number is less familiar. The Sun is not a fixed point in space. It is one of about 200 billion stars in the Milky Way galaxy, and it is, like every other star in our galaxy, in orbit around the galactic center. The orbit is enormous. The Sun lies about 26,000 light-years from the center of the galaxy, in the outer regions of one of the spiral arms, and it is moving along its orbit at about 230 kilometers per second. That is over 800,000 kilometers per hour. The full circuit takes about 230 million years. Our solar system has completed about 20 such orbits since the planet first formed, 4.5 billion years ago. Dinosaurs walked the Earth during the last one. The galactic year, the time required for the Sun to complete one trip around the galaxy, is so long that the entire age of mammals has occupied less than a single one of them. And there is yet a fourth motion, larger still. The Milky Way as a whole, with all its stars and gas and dark matter, is not at rest. The galaxy is moving through intergalactic space, pulled by the gravity of its neighbors, and by larger structures of mass we will come to. The most precise measurements of our galaxy's motion are made against the cosmic microwave background, the faint glow of light from the early universe that fills the sky in all directions. From the slight unevenness in the temperature of this glow, astronomers can read out the speed and direction of our galaxy's motion through the cosmos. The number is about 600 kilometers per second in the direction of the constellation Leo. By the time you finish watching this video, the Milky Way will have moved another few 100,000 kilometers in that direction. By the time you go to sleep tonight, the galaxy will have drifted by a distance about 3 times the size of the Earth. Add up all of these motions: the rotation of the planet, the orbit around the Sun, the orbit around the galactic center, the drift of the galaxy through the cosmos. Each of them adds a different velocity in a different direction, and the total motion of your body through space, right now, is something approaching 2 million kilometers per hour. This is not a metaphor or an exaggeration. It is the simple sum of the speeds at which the various structures you are part of are moving through the universe. You are, in a strict and measurable sense, traveling about 1 million miles an hour in a direction you cannot feel, through a void you cannot see. It is worth holding the number for a moment, because the immediate reaction tends to be disbelief, and the disbelief is itself a clue to something interesting. If a person were strapped to the outside of a fighter jet traveling at 2,000 kilometers per hour, the experience would be immediate and overwhelming. The wind, the sound, the cold, the pressure. Yet here you are, sitting in a chair, moving 1,000 times faster than that jet, with no awareness of it at all. The difference is not that the speed is less real. It is that the speed is shared with everything around you, and that there is no medium of air to push against, and that the motion is so smooth that no inertial sensor in your body has any way to detect it. The universe permits speeds that would be unimaginable on Earth, precisely because, at cosmic scales, the conditions that would make those speeds noticeable simply do not exist. And the only reason you do not notice any of it is that nothing in your immediate surroundings is moving differently. You share the motion. Your body and the chair you are sitting on, and the room around you and the city you live in are all riding along on the same planet, in the same orbit, in the same galactic arm, in the same galaxy, drifting through the same cosmic neighborhood. There is no friction, because most of space is empty. There is no resistance, because the motions are uniform on the scales that matter. There is no wind, because the universe is not a thing you move through, but a geometry in which you happen to be embedded. Stillness is not the actual state of anything. It is what motion looks like when it is shared. There is a particular thought experiment, an old one, that makes this concrete. Imagine you are in a sealed cabin below the deck of a smoothly sailing ship, in calm water, with no view of the outside. There is a fly in the cabin. There is a bowl of water on a table. There are some objects you can throw against the cabin's walls. Galileo, who first formulated the argument in 1632, asked whether you could perform any experiment inside that cabin that would tell you whether the ship was moving or sitting at the dock. His answer was no. The fly would fly the same way. The water would not slosh. A ball thrown against the forward wall would arrive with the same force as one thrown against the rear. As long as the ship moved smoothly and uniformly, no test conducted inside the cabin could distinguish motion from rest. This is true of every smoothly moving frame in the universe, and the Earth is such a frame, and the solar system is such a frame, and the galaxy is such a frame. You cannot tell from inside that you are moving. You can only deduce it from looking at things outside. This is the central fact this video is going to follow. Motion is not an interruption of stillness. It is the underlying condition of everything. The cosmos is not a quiet arrangement of fixed structures with occasional disturbances. It is a continuous interplay of nested motions, each layered into a larger one, each held in place by gravity and inertia, in ways that produce stable patterns rather than chaos. The night sky looks still because human senses cannot detect the kinds of motion that dominate the universe. The motion is there. It has been there since the beginning. It is the rule, not the exception. The motions are also extraordinarily reliable. The Earth has been orbiting the Sun at very nearly its present speed for 4.5 billion years, with the orbital period drifting only by tiny fractions over geological time. The Sun has been orbiting the center of the galaxy for the same length of time on a nearly stable path. The Milky Way has been drifting through intergalactic space for longer still. The night sky we see, with its familiar constellations, is essentially the same sky that humans saw 100,000 years ago, because the motions that change the sky are slow compared to a human life. What we are looking at when we look up at night is the result of motions that have been going on steadily and quietly for periods of time so long that the entire history of our species is a brief moment within them. To follow it carefully, we have to start with the very simplest fact about motion, which is that once something is moving, it tends to keep moving. This is not obvious from everyday experience, because everyday experience happens in a world full of friction. A ball rolled across grass slows down and stops. A puck slid across ice goes much further before stopping. A spacecraft launched into empty space, with nothing to brake against, simply continues. The further the friction is reduced, the longer the motion lasts. In the empty space of the cosmos, friction is so close to zero that motion can persist for billions of years without significant change. This is why the Earth has continued to orbit the Sun for 4.5 billion years without slowing, and why the Sun has continued to orbit the galactic center for the same length of time, and why the Milky Way has continued to drift through the universe since long before our solar system existed. Nothing is needed to keep these motions going. They simply persist. The patient understanding of this fact, that motion is the natural state of things in the absence of friction, took a long time for human thinkers to reach. For most of recorded history, the assumption was the opposite. Aristotle and many who followed him argued that motion required a constant cause, that any object set in motion would naturally come to rest unless something kept pushing it. This view fit everyday experience well enough, because everyday experience is full of friction. It took the work of Galileo in the early 17th century, and Newton later in the same century, to recognize that the friction was the exception and the persistence of motion was the rule. With that recognition, the heavens became explicable. The endless orbits of the planets, the silent drift of the stars, the unflagging spin of the Earth, all of it followed from a single simple principle. Once moving, things keep moving. And to see why, we have to step back briefly into the physics that makes the rest of the universe comprehensible. The principle has a name. It is called inertia. And the cleanest statement of it was given by Isaac Newton in the opening pages of his Mathematical Principles of Natural Philosophy, published in 1687. Newton put it as the first of 3 laws of motion. Every object continues in its state of rest or of uniform motion in a straight line, unless acted upon by an external force. In the centuries since, this single sentence has been confirmed by every experiment that has ever tested it. Nothing in the universe slows down on its own. Nothing speeds up on its own. Nothing changes direction on its own. To alter the motion of any object in any way requires a force, and the change is exactly proportional to the strength of the force applied. This is the law that explains why the cosmos stays in motion. Once a planet is set in orbit, it continues. Once a galaxy is spinning, it spins. Once a cloud of gas is drifting through interstellar space, it drifts. The motions do not need to be maintained. They are not powered by some hidden engine that could, in principle, run down. They are the default state of any object not being pushed or pulled by something else. And in the vast emptiness between stars, very few things are being pushed or pulled. Gravity acts at a distance, slowly bending paths over millions of years, but there is no friction. There is no resistance. There is no air. There is no medium against which to slow down. The empty space between stars is genuinely empty by Earth standards. In a cubic centimeter of the air in your room, there are about 25 quintillion molecules. In a cubic centimeter of typical interstellar space within our galaxy, there is on average less than one atom. Between galaxies, in the great voids that make up most of the volume of the universe, the density is lower still. The vacuums achieved by the best laboratory equipment on Earth, used in particle physics experiments, are dense by comparison with intergalactic space. A spacecraft drifting between stars encounters so few atoms per second that the cumulative force of their impact is, for all practical purposes, nothing. The Voyager probes have been flying through this near emptiness for nearly half a century, and their speed has not measurably changed. This is what makes Newton's first law a true description of the universe, rather than just a useful approximation. On the Earth's surface, in the presence of air, water, friction, and contact forces, the law looks like an idealization. Things stopped without continuous pushing all the time. But the law is not an idealization. The friction is the exception. The interstellar void is the rule. Most of the matter in the universe, by mass and by volume, lives in conditions where Newton's first law is approximately exact, and the motions of stars and gas clouds and galaxies persist for billions of years without slowing. The second of Newton's laws is also worth a moment, because it bears directly on how all the orbital motions of the cosmos are maintained. The law states that the acceleration of an object is proportional to the force applied to it, divided by its mass. A small force on a large object produces a small change in motion. A large force on a small object produces a large change. This is the law that quantifies the relationship between forces and motion. It explains why a baseball thrown with the same force as a bowling ball will travel much faster, and why the same gravitational pull will accelerate a feather and a hammer at the same rate if no air resistance opposes them. Apollo astronaut David Scott actually performed this demonstration on the surface of the Moon in 1971, dropping a hammer and a falcon feather simultaneously from the same height, and they hit the lunar surface at the same instant. Without air to slow the feather, both fell under the same gravitational acceleration, exactly as Galileo had predicted 3.5 centuries earlier. The third law completes the picture. Every action has an equal and opposite reaction. If one object pushes on another, the second pushes back with equal force in the opposite direction. This is the principle that makes rockets possible. A rocket pushes exhaust gases backward, and the gases push the rocket forward with equal force. It is also the principle that explains how gravitational attractions work in the cosmos. The Earth pulls on the Sun with exactly the same force with which the Sun pulls on the Earth. The two bodies do not actually orbit each other in a simple sense. They orbit their common center of mass. Because the Sun is so much more massive than the Earth, that center of mass lies very close to the center of the Sun, but it does not lie exactly at the Sun's center. The Sun wobbles slightly, as the Earth swings around it, and the same is true of every star with planets. This is how astronomers now find planets around other stars, by watching the slight wobble of distant stars as their unseen planets pull on them. These three laws, together with Newton's separate law of gravity, are enough to describe almost every motion visible in the cosmos. The law of gravity itself is simple to state. Every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Two objects twice as massive attract with 4 times the force. Two objects twice as far apart attract with 1/4 the force. The inverse square dependence on distance is what makes gravity weaken with distance, and it is what makes the long-range behavior of gravity over cosmic distances different from short-range forces like electromagnetism in atoms. With these tools, Newton was able to explain something that had puzzled astronomers since antiquity. Why do the planets orbit the sun in the patterns they do? The answer, Newton showed, is that the gravity of the sun bends every planet's natural straight-line motion into a curve. Without the sun's gravity, a planet moving through space would simply travel in a straight line forever. With the sun's gravity, the planet is continuously pulled toward the sun, and the combination of its forward motion and the inward pull produces an ellipse. The exact shape of the ellipse depends on how fast the planet is moving and how strong the gravitational pull is. Slow planets, deep in the sun's gravity, trace tight orbits close to the star. Fast planets, far from the sun, trace wide orbits that take longer to complete. Both extremes obey the same single law. The image to hold is this. Imagine throwing a baseball horizontally from the top of a very tall tower. The ball travels forward for a while and then falls to the ground, the path bent into a curve by Earth's gravity. Now throw it harder. The ball goes further before it falls. Now throw it much harder. Hard enough that the surface of the Earth curves away beneath it as fast as it falls toward the surface. The ball will never reach the ground. It will fall around the Earth forever, in what is called an orbit. This is exactly what every satellite, every moon, every planet is doing. They are not held up by any support. They are falling continuously, but moving sideways fast enough that they keep missing the thing they are falling toward. Newton himself illustrated this with a drawing of a cannon on a mountaintop, firing balls at increasing speeds, and showed that at a particular speed, the cannonball would simply enter orbit. The principle is the same for the International Space Station, for the Moon, for the Earth around the Sun, and for the Sun around the center of the galaxy. Orbits are not a special kind of motion. They are falls that miss. Energy is the other concept worth introducing briefly here, because it tells us why motions persist even when they appear to slow down. Energy in physics is a quantity that in any closed system cannot be created or destroyed. It can only change form. A planet orbiting the sun has a particular amount of kinetic energy, which is the energy of motion, and a particular amount of potential energy, which is the energy stored in its gravitational relationship with the sun. As the planet moves through its orbit, the two quantities trade off against each other. Near the sun, the planet moves fast, with high kinetic energy and low potential energy. Far from the sun, it moves more slowly, with lower kinetic energy and higher potential energy. The total is conserved. The planet does not need any external supply of energy to keep going, because nothing is being lost. This conservation extends to every motion in the cosmos. A spinning galaxy has angular momentum, which is the rotational equivalent of straight-line motion. And the angular momentum is conserved unless something acts on the galaxy from outside. A cloud of gas collapsing under its own gravity converts its potential energy into the kinetic energy of inward falling material and the thermal energy of compression-heated atoms. A planet's orbital energy is conserved over billions of years, with only tiny adjustments from the slight tides it raises in the sun. The numbers stay in books. The universe keeps its energy ledger balanced, and the motions continue because they are the natural consequence of that conservation. It is worth pausing to consider how much energy is involved in even the most ordinary cosmic motion. The kinetic energy of the Earth's orbit around the Sun is staggering. It is the energy required to push a 6 trillion kilogram planet around its track at 30 kilometers per second, and the number that falls out of the calculation is roughly 2.5 times 10 to the 33rd joules. For comparison, the total energy consumed by human civilization in a year, all of it, every power plant and engine and battery, is about 610 to the 20th joules. The Earth's orbital energy is, in round numbers, 4 trillion times the annual energy consumption of our entire species. To stop the planet in its orbit would require an amount of energy so vast that no conceivable process within our reach could produce it. The orbit is, in this sense, essentially permanent. The same is true of the Sun's orbit around the galaxy, of the rotation of the Milky Way, of the drift of every star and every cloud of gas in the cosmos. The motions are not just enduring. They are protected by such enormous reserves of energy that almost nothing can disturb them. There is a single exception to all of this, which becomes important at the largest scales of the cosmos. Einstein's general relativity, published in 1915, refines Newton's picture of gravity in ways that matter near very massive objects and over cosmological distances. In Einstein's picture, gravity is not a force in the usual sense. It is the curvature of space-time itself, caused by the presence of mass and energy, and what we feel as the pull of gravity is the natural tendency of any moving object to follow the curved geometry around heavy things. For ordinary motions of planets and stars, Einstein's picture gives the same answers as Newton's, to extremely high precision. The two theories diverge only in extreme cases, near black holes, near neutron stars, and over the expanding universe as a whole. Einstein's picture takes over, and Newton's becomes only an approximation. For everything else, the older Newtonian picture is the one we will rely on, because it gives accurate answers, and it is the one whose intuitions match ordinary experience. What follows from all of this is a universe in which motion is the natural state. Not because anything pushes it, not because the cosmos requires renewal, simply because, once moving, nothing stops without a reason to stop. And very little of the universe contains anything that could provide such a reason. The cosmos is in motion because that is what objects do, in the absence of friction, in a space so empty that friction has nowhere to act. Once Newton had stated this clearly, the long argument about whether the heavens needed constant attention to keep moving was over. The heavens did not need attention. They had been left to themselves, and what they did, left to themselves, was continue. This sets the stage for everything that follows. The Earth keeps spinning because it was set spinning long ago, and nothing has stopped it. The planets keep orbiting because they were set in motion, and the Sun's gravity merely bends them into curves. The galaxy keeps rotating because the original cloud that formed it was rotating, and the rotation has been preserved by the conservation of angular momentum ever since. The expansion of the universe continues because it began long ago, and the geometry of space is still adjusting in response. Every motion in the cosmos is a continuation of something that started in the distant past and has, by the simple laws just laid out, continued ever since. The clearest place to begin watching this in detail is the smallest and most familiar layer of all, the planet beneath our feet. It is the one we know best, and the one in which the layered motions of the universe first become visible to anyone who looks carefully. The planet has been spinning for as long as it has existed. The rotation began when the Earth first formed, 4.5 billion years ago, out of a swirling disk of gas and dust orbiting the young sun. That disk was itself rotating, the leftover spin of the larger interstellar cloud from which the entire solar system condensed. When the disk collapsed inward to form the planets, the rotation was preserved by the same principle that makes an ice skater spin faster when she pulls her arms in. The original slow swirl of an enormous cloud became, as the matter contracted, the rapid spin of much smaller bodies. The Earth ended up with one full rotation every 24 hours, and it has been keeping very close to that rate ever since. The rate is not, in fact, perfectly constant. The Earth's rotation is gradually slowing down by tiny amounts over geological time. The cause is the Moon. The Moon's gravity raises tides not just in the oceans, but in the solid body of the Earth itself, and the friction of those tides drags very slightly against the planet's spin. The drag is feeble, but over billions of years it accumulates. When the Earth was young, just after the Moon formed, the day was only about 6 hours long. The planet spun 4 times faster than it does now, and the Moon hung much closer in the sky. As the Moon's tides slowly siphoned rotational energy from the planet, the day lengthened and the Moon was pushed gradually outward into a wider orbit. The Moon today is about 38 centimeters further from the Earth every year, a recession measured directly by reflecting laser beams off mirrors left on the lunar surface by the Apollo astronauts in the 1960s and 70s. The Earth has been slowing and the Moon has been retreating for as long as both have existed. The rotation also shapes the planet itself. The Earth is not a perfect sphere, but a slightly flattened one, wider at the equator than from pole to pole. The difference is small but measurable. The equatorial radius is about 6,378 kilometers. The polar radius is about 6,357 kilometers. The difference, 21 kilometers, is the amount by which the equator bulges outward beyond a sphere that would just touch the poles. The cause is the rotation. Material at the equator is being carried along at over 1,600 kilometers per hour, and the tendency of that material to fly outward in a straight line, which it would do if gravity did not hold it down, gives the planet a measurable bulge around its middle. The same thing happens to every rotating body. Jupiter, which rotates much faster than the Earth, completing a day in less than 10 hours, is visibly oblate when seen through a telescope, with an equatorial diameter about 7% larger than its polar diameter. Saturn, faster still, is more oblate yet. Every rotating planet wears its rotation in the shape of its body. The same principle that makes the Earth's rotation persist also makes it remarkably stable in direction. The spin axis of the planet, the imaginary line passing from the South Pole through the planet to the North Pole, points in a particular direction in space, very close to the star we call Polaris. It has pointed in roughly that direction for the whole of human history. The reason is that any spinning body resists changes in the direction of its spin axis. This is the same principle that makes a spinning top stand upright, that makes a bicycle easier to balance when moving than when standing still, and that allows a gyroscope to hold its orientation while everything around it rotates. The Earth, in this sense, is a vast gyroscope. The angular momentum of its rotation acts to keep the spin axis pointing steadily into space, decade after decade, century after century. The pointing is not entirely fixed, however. The Earth's spin axis traces a very slow circle in the sky, completing one full loop every 26,000 years. This motion is called precession, and it is caused by the Sun and the Moon pulling slightly on the Earth's equatorial bulge. The Earth is not a perfect sphere. It is slightly flattened at the poles and slightly bulged at the equator, a consequence of its rotation. And this bulge gives the Sun and the Moon something to pull against. The combined torque from those pulls makes the spin axis trace a circle in the sky, the way the axis of a wobbling top traces a small circle as the top slows down. Polaris is the pole star today, but it has not always been and will not always be. About 13,000 years from now, the pole will point in the direction of the star Vega, and Vega will be the pole star instead. The cycle continues. The same precession has been happening, slowly, for the entire history of the planet. The orbital motion is just as old and just as steady. The Earth has been falling around the Sun in essentially its present orbit for 4.5 billion years. The orbit is not a perfect circle. It is a slightly elongated ellipse, with the Sun sitting at one of the two focal points of the ellipse rather than at the geometric center. The Earth is about 3% closer to the Sun at its nearest point, called perihelion, than at its furthest, called aphelion. The closest approach happens in early January each year, and the furthest point in early July. The difference is small enough that it does not directly cause the seasons. The seasons are caused by something else, by the fact that the Earth's spin axis is tilted with respect to the plane of its orbit by about 23.5 degrees. This tilt is the reason that one hemisphere is pointed toward the Sun for half of the year and away from the Sun for the other half, and the reason that summer and winter alternate as the planet moves around its orbit. The tilt is, like the spin axis itself, essentially fixed, but with a slow wobble of its own. Over a period of about 41,000 years, the tilt varies between roughly 22 and 24.5 degrees, and the variation has measurable effects on the climate. This is one of several long, slow rhythms in the Earth's orbit that, combined with the precession of the axis, have driven the slow cycles of ice ages and warm periods throughout the planet's history. The Serbian astronomer Milutin Milankovic worked out the mathematics of these orbital variations in the early 20th century. While interned as a prisoner of war during the First World War, and the cycles now bear his name, his calculations predicted the timing of the major ice ages of the past several 100,000 years with extraordinary precision, a prediction subsequently confirmed by direct measurements of ancient climate recorded in ocean sediment cores and ice cores from Greenland and Antarctica. The slow tilting and untilting of the Earth's axis, the gradual shifts in the shape of its orbit, the precession of the equinoxes, all of these motions are real. All of them are continuous, and all of them shape the climate the planet experiences as the centuries unfold. There is yet another orbital motion to mention, this one shared with the Moon. The Earth and the Moon do not quite orbit each other in a simple sense, just as the Earth and the Sun do not. The two bodies orbit their common center of mass, which is a point about 4,700 kilometers from the Earth's center, well inside the planet itself, but not at its center. As the Moon swings around the Earth once every 27 days or so, the Earth wobbles around this shared center, tracing a small circle of its own. The wobble is small enough that, viewed from a great distance, the system looks like the Moon orbiting a steady Earth. But up close, the Earth itself is moving, in a tight loop around a point about 3/4 of the way from its center to its surface. This is the same principle that astronomers use to detect planets around other stars. The stars wobble, very slightly, around the centers of mass of their planetary systems, and the wobble can be measured. The combined picture of the Earth-Moon system, then, is two bodies dancing around a shared invisible point in space, while that point itself sweeps along the orbit around the Sun. The Moon traces a path that is not quite a circle around the Earth, because the Earth itself is moving. From the Sun's perspective, the Moon's actual trajectory through space is a slightly wavy curve that follows the Earth's orbital ellipse, sometimes a little ahead of the Earth, sometimes a little behind, weaving back and forth as the two bodies swing around each other on their way around the star. Neither body is ever standing still in any absolute sense. They are partners in a continuous motion that has been going on since they first formed, locked together by gravity, drifting around the Sun at 30 kilometers per second, and individually circling each other at about a kilometer per second on top of that. The orbital speed of the Earth is not constant either. It is slower at aphelion in July, and faster at perihelion in January, because the planet is closer to the Sun in January, and the Sun's gravity is stronger there. At perihelion, the Earth moves at about 30.3 kilometers per second. At aphelion, the speed drops to about 29.3 kilometers per second. The difference is small, only about a kilometer per second across the year, but it is real, and it shapes how long the seasons are. The northern hemisphere's summer, which happens when the Earth is near aphelion and moving more slowly, is in fact a few days longer than its winter, because the planet spends a few extra days traversing the part of the orbit where it is moving slowest. Most people in temperate latitudes have noticed that the months between the spring and autumn equinoxes feel longer than the months between the autumn and spring ones. The feeling is correct. The orbit makes it so. The exact relationship was worked out by the German astronomer Johannes Kepler in the early 17th century, 3 generations before Newton. Kepler's 3 laws of planetary motion, derived empirically from years of careful observations made by his predecessor Tycho Brahe, state that planets orbit in ellipses, that they sweep out equal areas in equal times, and that the square of the orbital period is proportional to the cube of the orbit's average radius. The second of these laws is, in effect, a description of how orbital speed varies. A planet sweeps out the same area of its orbit each month, which means that when the planet is close to the Sun and tracing a short, fast arc, it must be moving quickly to cover the same area as when it is far from the Sun, tracing a long, slow arc. Newton later showed that all 3 of Kepler's laws fall out as direct consequences of his own laws of motion, combined with his law of gravity. But Kepler had found them first, by patient comparison of theory with data, decades before the underlying physics was understood. The Earth's orbital motion, like its rotation, has been remarkably stable for the entire history of the planet. The orbit's shape varies very slightly over time, mostly in response to the gravitational pulls of Jupiter and the other planets, but the variations are small and predictable. Calculations done with modern computers can extend the Earth's orbital history backward and forward by tens of millions of years before the chaos of small interactions makes precise prediction impossible. Within those limits, the orbit is essentially clockwork. The Earth completes a journey around the Sun once a year, traces an ellipse close to the one it traced last year, and will trace a very similar one again next year. Now consider what is actually happening when you stand outside on a clear evening and look up. You are riding a spinning planet whose surface is moving eastward beneath your feet at 1,000 kilometers per hour. You are riding an orbiting planet whose entire mass is sweeping around the Sun at 30 kilometers per second. You are riding a wobbling planet whose axis traces a vast slow circle in the sky over 26,000 years. You are riding a tilting planet whose spin axis nods through small variations over 41,000 years. You are riding a planet that wobbles slightly around its own center of mass with the Moon. And all of this is happening at once, smoothly, without resistance, without effort, without anything pushing or pulling against it. The Earth simply continues, by the same principle that keeps any object in motion when nothing acts to slow it down. These are the motions of a single planet. They are real, they are measurable, they have been continuous for billions of years, and they unfold within an envelope of much larger motions still. The Sun itself, around which the Earth orbits, is on its own journey through the galaxy, and that journey is even more dramatic than the planetary motions we have just walked through. But the Sun does not travel alone. It carries with it a family of worlds, each on its own orbit, each circling at its own pace, each performing a small piece of the same slow, patient dance that has shaped the solar neighborhood for as long as anything has been there to see it. There are 8 planets, and after them a swarm of smaller worlds. And beyond that, a great cold reservoir of icy bodies that reaches out into the dark for thousands of times the distance from the Earth to the Sun. All of it is moving. All of it has been moving for 4.5 billion years. The planets trace orbits whose periods range from a few months for the innermost world to nearly 2.5 centuries for the outermost. The smaller bodies drift in patterns of their own, some on orbits, not much different from the planets. Others on long looping paths that swing them out into the cold and back in toward the sun's heat over thousands or millions of years. The sun itself, the gravitational anchor of the whole arrangement, is also moving, drifting through the galaxy at over 200 kilometers per second, carrying every world that orbits it along on the journey. Begin at the sun's nearest companion, Mercury. It is the smallest of the planets, the closest to the sun, and the fastest. It orbits at about 48 kilometers per second, completing one full circuit every 88 Earth days. Its orbital speed is, on average, 60% higher than the Earth's, because it lies deeper in the sun's gravitational well and has to move faster to maintain a stable orbit. Mercury also has the most elongated orbit of any of the planets, a noticeably elliptical loop that takes the planet from 46 million kilometers from the sun at its closest approach to 70 million at its furthest. The orbital speed varies dramatically across the journey, ranging from about 39 kilometers per second at the aphelion to nearly 59 at the perihelion. Mercury sweeps closer to the sun than any other world and feels its gravity more strongly, and moves accordingly faster to stay in orbit. Venus comes next. It orbits at about 35 kilometers per second, completing a circuit every 225 days. Its orbit is the most circular of any of the planets, almost a perfect circle, with the distance from the sun varying by less than 1% across the year. Venus is also peculiar in one respect that has no good explanation in current models of how planets form. It rotates backward. Almost every other body in the solar system, including all the other planets and the sun itself, rotates in the same direction it orbits, the leftover sense of rotation from the original gas cloud that gave rise to the entire system. Venus spins in the opposite direction, very slowly, completing one rotation every 243 Earth days. A day on Venus is longer than a year on Venus. The most likely explanation involves a catastrophic collision early in the planet's history that knocked it onto its current backward spin, but no one is entirely sure. Whatever the cause, the rotation has been continuing in this direction ever since, in the smooth persistence of motion that nothing in the universe slows down for free. The Earth is the third world, and its motions are the ones we already know best, so the description here can be brief. The planet orbits at about 30 kilometers per second on a slightly elliptical path, with the Moon as its companion. The Earth and the Moon are unusual among the planets in being so closely matched in size. The Moon is about a quarter the diameter of the Earth, making the Earth-Moon system more of a double planet than a planet with a satellite. Most of the other moons in the solar system are far smaller compared to their parent planets. The Moon's size and its proximity are the reason it has such a large influence on the Earth's tides and rotation. Mars is the fourth. It orbits at about 24 kilometers per second, completing one circuit every 687 Earth days, which is about 1 Earth year and 10 months. Its orbit is moderately elliptical, similar to Mercury's but less extreme. The Martian day, the time required for Mars to complete one rotation on its axis, is about 24 hours and 37 minutes, almost identical to Earth's. The Martian axial tilt is also similar to Earth's, about 25 degrees against the plane of its orbit, so Mars has seasons that resemble ours in pattern, though not in temperature. Mars carries two small companions of its own, Phobos and Deimos, both irregularly shaped rocks captured at some point in the planet's history, both orbiting much closer to Mars than the Moon does to the Earth. Phobos orbits so close and so fast that it completes one full circuit around Mars in less than 8 hours, faster than Mars itself rotates. From the Martian surface, Phobos would be seen to rise in the west and set in the east, the only natural satellite in the solar system that would appear to do so. Between Mars and Jupiter lies the asteroid belt, a vast disk of rocky and metallic bodies, most of them small, none of them ever managing to consolidate into a planet because of the gravitational disruption of Jupiter just outside. The largest body in the belt, Ceres, is a dwarf planet about 1,000 kilometers across, and it carries about a third of the entire mass of the belt by itself. The next largest, Vesta and Pallas, are several hundred kilometers across. After them, the sizes drop off rapidly, with most of the bodies being kilometer-scale rocks and a great many even smaller fragments. Estimates of the total number of asteroids larger than a kilometer run into the millions. All of them orbit the Sun in roughly the same direction as the planets, completing one circuit every 3 to 6 years, depending on their distance. The total mass of the asteroid belt is, despite appearances in some illustrations, only about 4% of the mass of the Moon. The belt is not a crowded place. Spacecraft routinely fly through it without taking any special precautions, because the bodies are so far apart that the chance of striking one is essentially zero. Beyond the asteroid belt is Jupiter, the largest of the planets and a kind of solar system within a solar system. Jupiter is so massive that it would take about 318 Earths to balance it on a scale. It orbits at about 13 kilometers per second, completing one circuit around the Sun every 12 Earth years. Its rotation is the fastest of any of the planets. Jupiter completes one rotation on its axis in just under 10 hours, which means a point on its equator is sweeping along at about 45,000 kilometers per hour, faster than any spacecraft humans have ever launched. The rapid rotation has flattened the planet noticeably, giving it that distinctly oblate shape visible in any decent telescope. Jupiter also has at least 95 moons, 4 of them large enough to have been spotted by Galileo with one of the earliest telescopes in 1610. Io, Europa, Ganymede, and Callisto, the Galilean moons, each follow their own orbits around Jupiter at their own speeds, ranging from 42 hours for Io to about 2 weeks for Callisto. Ganymede is the largest moon in the solar system. It is larger than the planet Mercury, though far less massive, since it is made mostly of water ice rather than rock and iron. Saturn comes after Jupiter, orbiting at about 9 kilometers per second, with an orbital period of about 29.5 Earth years. Saturn is the second largest planet but the least dense. Its density is less than that of water. If you could find a bathtub large enough, Saturn would float in it. The famous rings of Saturn are a flat disk of icy and rocky particles in orbit around the planet, ranging from grains the size of dust to chunks the size of houses. The rings are extraordinarily thin compared to their diameter, about a meter thick across a span of 270,000 kilometers, like a sheet of paper the size of a city. Every particle in the rings is on its own orbit around Saturn, traveling at speeds determined by its distance from the planet, with the inner particles moving faster than the outer ones in accordance with Kepler's laws. The rings are not as old as Saturn itself. Recent analysis of data from the Cassini spacecraft, which orbited Saturn from 2004 until 2017, suggests that the rings formed only a few 100 million years ago, possibly from the breakup of a small icy moon. They are, on geological timescales, a temporary feature, and they will eventually be pulled into Saturn or scattered outward by the planet's gravity. Uranus, the seventh planet, orbits at about 6 8/10 kilometers per second, with an orbital period of 84 Earth years. It is famous among the planets for being tipped on its side. Its rotational axis is tilted about 98 degrees against the plane of its orbit, so that the planet effectively rolls along its orbit rather than spinning upright as the others do. The most likely cause is, as with Venus's backward rotation, a catastrophic collision early in the planet's history. Whatever the cause, the result is that Uranus has seasons that are unlike anything else in the solar system. Each of its poles spends about 42 Earth years in continuous sunlight, and the next 42 in continuous darkness, as the planet slowly tips through its long orbit around the Sun. Neptune, the eighth and outermost planet, orbits at about 5 4/10 kilometers per second, with an orbital period of 165 Earth years. It was discovered in 1846, not by direct observation, but by mathematical prediction. The orbit of Uranus had small irregularities that could not be explained by the gravity of the known planets, and Urbain Le Verrier in Paris calculated that another, more distant planet must be responsible. He sent his prediction to the Berlin Observatory, where Neptune was found within a degree of the predicted position on the very first night of looking. It remains one of the cleanest triumphs of theoretical physics applied to the cosmos, a planet discovered by reasoning before anyone had ever seen it through a telescope. Beyond Neptune lies the Kuiper Belt, a much larger and more distant cousin of the asteroid belt, populated mostly by icy bodies. Pluto, once considered a planet, is one of the largest members. It is about 2/3 the size of the Moon and orbits the Sun once every 248 Earth years, on an elliptical path so elongated that for 20 years out of every 248, Pluto is actually closer to the Sun than Neptune. This was last the case from 1979 until 1999. Pluto and Neptune do not collide because their orbits are tilted with respect to each other, and because they are locked in a gravitational resonance that ensures they never come close. The Kuiper Belt contains many other dwarf planets and an estimated trillion or so smaller bodies, all in slow orbits around the Sun. The New Horizons spacecraft, launched in 2006, flew past Pluto in 2015 and continued outward to study a small Kuiper Belt object called Arrokoth in 2019. It is still moving outward on its own slow trajectory through the outer solar system, in a journey that will eventually take it into interstellar space. Beyond even the Kuiper Belt, the most distant component of the solar system is something called the Oort cloud. This is a spherical shell of icy bodies, extending perhaps 100,000 times the Earth-Sun distance into space, far beyond anything we have ever directly observed. The Oort cloud is the reservoir from which long-period comets come. When one of the bodies in the cloud is perturbed by the gravity of a passing star, or by the larger structure of the galaxy, it can fall inward toward the Sun, swinging through the inner solar system on an orbit that takes thousands or millions of years to complete. The cloud is so distant that its outer regions are only loosely bound to the Sun, and bodies on its fringes drift on the borderline between belonging to the solar system and belonging to the open galaxy beyond. All of this is orbiting the Sun. And the Sun itself, around which all of this orbits, is itself moving. The solar system as a whole is being carried along on the Sun's orbit around the center of the galaxy at over 200 kilometers per second. The planets, the asteroids, the comets, the Kuiper Belt objects, the Oort cloud are all being swept along with the Sun on a journey that takes more than 200 million years to complete. The whole arrangement is, in a strict sense, a small piece of moving matter following a much larger trajectory through a much larger gravitational landscape. The orbits of the planets around the Sun, when seen from outside the solar system over very long time intervals, would not appear as simple closed loops. They would appear as long helical spirals, traced through space as the entire system glides along its galactic path. We are spiraling, slowly and steadily, in a direction the night sky can almost reveal if you know where to look. The point in the sky toward which the Sun is moving is called the solar apex, and it lies in the constellation Hercules, near the bright star Vega. We are moving in that direction, at over 200 kilometers per second, relative to the average motion of nearby stars. Astronomers measured this in the 18th century by Sir William Herschel, who noticed that nearby stars on average appeared to drift away from one part of the sky and toward the opposite part, just as objects ahead and behind a moving train seem to recede and approach. The solar apex points the direction of our motion through the local stellar neighborhood. We have been heading that way for as long as the Sun has been carrying its planets along on the galactic orbit, and we will continue to head that way for tens of millions of years more before the slow curve of the galactic orbit eventually bends the direction of motion elsewhere. The motion of the solar system, then, is not just the inward dance of the planets around their star. It is also the outward sweep of the entire system through the galaxy, carrying its worlds along on a much larger curve. The patterns lock together. The smaller motions inside the system are bound by the Sun's gravity. The larger motion of the whole system through the galaxy is bound by the gravity of the galaxy itself. The combined pull of hundreds of billions of other stars and the dark matter that surrounds them. Each layer of motion holds together within the next layer above it, and each follows the same simple physical principles that govern any object moving under gravity. The Sun's family is one small participant in something vastly larger, and that larger thing has motions of its own that dwarf anything the planets are doing. The Milky Way is one galaxy among perhaps 2 trillion in the observable universe, and it is the one in which we happen to live. From the inside, we cannot see it whole. The Sun sits well out in one of the spiral arms, 26,000 light-years from the galactic center, and the densest part of the galaxy, the central bulge, sits in the direction of the constellation Sagittarius. On a clear night, away from city lights, the Milky Way appears across the sky as a faint band of pale light, a soft river running from horizon to horizon. The light is the combined glow of hundreds of billions of stars too faint and too distant to see individually, blurred together by the eye into a single continuous brightness. The galaxy is a vast flattened disk of stars and gas and dust, about 100,000 light-years across, and only about 1,000 light-years thick. And we are looking at it from the inside, edge on. All of it is in motion. Every star, every gas cloud, every speck of dust in the Milky Way is orbiting the galactic center, on its own path, at its own speed. The combined motion is the rotation of the galaxy as a whole, a vast slow turning that takes hundreds of millions of years to complete a single circuit, even though the individual stars within the disk are moving at hundreds of kilometers per second. The galaxy is, in this sense, an enormous spinning structure, held together by gravity, organized by rotation, drifting through intergalactic space as a single coherent thing while its components circle inside it. The Sun's orbit around the galactic center takes about 230 million years. The orbital speed is about 230 kilometers per second, which is to say that every second of every day, the Sun and the Earth and all the planets and the moons and the asteroids and the entire solar system is moving along this galactic orbit by a distance greater than the diameter of the United States. In an hour, the solar system traverses more than 800,000 kilometers along the galactic path. In a year, the distance covered is over 7 billion kilometers, more than 10 times the distance from the Sun to Saturn. And yet, despite these enormous distances, the galaxy is so large that the Sun has completed only about 20 orbits since the solar system first formed. The galactic year, the time required for a single trip around the galaxy, is so long that the entire history of life on Earth has unfolded across only the most recent few of them. The Milky Way is not a uniform disk. It has structure. There are spiral arms, the bright lanes of star formation, and young blue stars that trace curving patterns from the central bulge outward to the edge of the disk. There are 4 major arms, with smaller spurs and offshoots, and the Sun lies on one of the smaller spurs, called the Orion arm or the local spur, which sits between 2 of the major arms. The spiral pattern is not, as one might first assume, made of fixed lanes of stars that rotate together as the galaxy turns. The arms are something stranger. They are density waves, regions where stars and gas are momentarily concentrated as they pass through, the same way a traffic jam on a highway moves as a wave through the line of cars without the individual cars staying in the jam. The stars themselves orbit the galactic center at speeds determined by their distance from the center. When they enter a spiral arm, they slow slightly, pile up briefly, and continue. The arm pattern moves around the galaxy at its own pace, slower than the stars themselves. Individual stars drift in and out of the arms as they complete their orbits, while the arms persist as patterns rather than as collections of fixed material. The bright appearance of the spiral arms comes mostly from young blue stars and from the glowing clouds of gas being compressed into new stars as they pass through. The arms are sites of active star formation, where the temporary increase in density triggers the gravitational collapse of gas clouds into new stellar nurseries. Star clusters form, blaze brightly for a few million years, and disperse as their member stars drift apart in slightly different orbits. The bright young stars are short-lived, lasting only a few million to a few tens of millions of years, so they remain close to where they were born. The longer-lived stars, including the Sun, drift away from their birth arms over billions of years and end up scattered throughout the disk, with no clear memory of where they originated. The motion of the Sun through the galactic disk is not perfectly circular. The Sun's orbit has a small inward and outward oscillation, taking it a little closer to the galactic center and then a little further out, with a period of about 170 million years. It also has a small vertical oscillation, taking it slightly above and below the plane of the disk, with a period of about 66 million years. The Sun is currently above the central plane of the disk by about 50 light-years, and is moving slowly downward toward the plane, which it will cross in another 30 million years or so. These small motions are superposed on the larger orbital motion around the galactic center, and they give the Sun's path through the galaxy a slightly wavy, slightly elliptical character rather than a clean circle. The center of the galaxy, around which everything orbits, is dominated by a single object that contains 4 million times the mass of the Sun, packed into a region smaller than our solar system. It is a supermassive black hole called Sagittarius A star in the catalog, and it sits motionless at the dynamical center of the entire structure. The black hole is not what holds the galaxy together, however. Its gravity dominates only the central few light-years. Beyond that, the gravity of all the other matter in the galaxy takes over, and the rotation of the disk is determined by the combined mass of everything inside any given orbit, not by the central black hole alone. The black hole is the still point at the heart of the spinning galaxy, but the galaxy's structure is shaped by the distributed mass of its stars and gas and the much greater mass of something far stranger. That something is dark matter, and its existence was first deduced from the rotation of galaxies. In the 1970s, the American astronomer Vera Rubin, working with her colleague Kent Ford at the Carnegie Institution in Washington, made careful measurements of how fast stars and gas were orbiting in galaxies beyond our own. She used the Doppler shifts in the light of stars at different distances from the galactic centers to measure their orbital speeds, and she found something deeply puzzling. The outer parts of the galaxies were orbiting much too fast. By Newton's laws of gravity applied to the visible mass of the galaxies, the outer stars should have been slowing down as the distance from the center increased, just as the outer planets in our solar system move more slowly than the inner ones. But they were not slowing. The orbital speeds remained roughly constant out to the visible edge of every galaxy Rubin measured and beyond, into the diffuse outer regions where almost no stars existed at all. This could only mean one thing. There was a great deal of mass in those galaxies that was not visible. Mass that did not emit light. Mass that did not absorb light. Mass that interacted with the rest of the galaxy through gravity and nothing else. The amount of this dark mass turned out to be about 6 times the amount of all the ordinary matter in the galaxy combined. 6/7 of the mass of every galaxy was invisible, and it was arranged in a roughly spherical halo extending well beyond the visible disk, with the visible matter sitting embedded inside it like a coin in the center of a much larger soap bubble. Without the dark matter, the galaxy would fly apart. The outer stars are moving fast enough that the visible mass cannot hold onto them by itself. Only the gravity of the surrounding halo of dark matter keeps the galaxy bound together as it rotates. The shape of what Rubin and Ford were measuring deserves a moment of attention, because it is one of the cleanest pieces of evidence for dark matter that exists. If you plot the orbital speeds of stars against their distance from the galactic center, you get what astronomers call a rotation curve. For our solar system, the rotation curve follows Kepler's laws and falls off as you move outward. The Earth moves at 30 kilometers per second, Jupiter at 13, Neptune at 5. The further from the Sun, the slower. This is the expected behavior for any system where the central mass dominates and the outer orbiters are pulled inward by gravity that weakens with distance. When Rubin plotted the rotation curve of the Andromeda galaxy, and then of dozens of other galaxies, she expected the same shape. What she found instead was a curve that climbed rapidly with distance from the center, then flattened, then stayed flat all the way out to the edge of the visible disk and beyond. The stars at the outer edge were moving just as fast as the stars halfway in. The expected fall-off was nowhere. The simplest explanation was that the gravity holding the outer stars in orbit was not coming only from the visible matter near the center. It was coming from a vast distributed cloud of unseen mass that extended out far beyond the bright disk. The existence of dark matter has been confirmed many times since Rubin's original measurements by independent lines of evidence ranging from the bending of light by galaxy clusters to the patterns of the cosmic microwave background. What it is made of remains unknown. It is not made of any of the particles known to ordinary physics. It is some new kind of matter that fills the halo of every galaxy, including ours, and shapes the rotation of every galactic disk through its silent gravitational pull. The motion of the Sun around the center of the Milky Way is in large part a response to the gravity of dark matter that no one has ever directly observed. The galaxy itself, the disk and the bulge and the halo, is not a static structure even on the longest timescales. It is slowly evolving. New stars are forming in the spiral arms. Old stars are dying and dispersing their material back into the interstellar medium. The disk is being gradually thickened by the accumulated effects of small disturbances over billions of years. The bulge is growing as material falls inward over time. The galaxy has been doing all of this for at least 10 billion years, since shortly after the universe itself began producing the first galaxies, and it will continue to do so for many billions of years more. The Milky Way has also grown by absorbing smaller galaxies. Astronomers have found, scattered through the disk and the halo, the remnants of perhaps a dozen or more smaller galaxies that the Milky Way has consumed over the course of its history. The most famous of these is the Gaia-Enceladus event, the merger with a galaxy about a quarter the mass of the Milky Way that happened roughly 10 billion years ago. The collision deposited a population of stars onto distinctively elliptical orbits, and those stars can still be identified today by their motions, even though the merger itself happened before the Earth existed. More recent and smaller mergers are still being unraveled. The Sagittarius dwarf galaxy, a small companion currently being torn apart by the Milky Way's gravity, is wrapped in long streams of stars trailing behind it like a comet's tail, leaving a record of its slow disintegration over the past billion years. Every star in the night sky, then, is on its own path. Some are stars that formed within the Milky Way's disk in their own corner of the spiral pattern. Some are former members of smaller galaxies that the Milky Way absorbed long ago, now orbiting in distinctive paths that mark their origin. Some are bound to the disk, others to the bulge, others to the halo. All of them are participating in the rotation of the galaxy, in their own ways, on their own orbital paths. The night sky we see is a snapshot of an enormous, slow, multi-layered rotation, frozen by the brevity of human life into apparent stillness. The galaxy as a whole, all of this structure and rotation and slow evolution, is also moving. We met this number earlier. The Milky Way is drifting through intergalactic space at about 600 kilometers per second in the direction of the constellation Leo, measured against the cosmic microwave background. This motion is not the rotation of the galaxy. It is the motion of the entire galactic structure as a single object through space. And it is not a random drift. It is a fall, directed by the gravity of larger structures in the universe beyond the Milky Way. We are being pulled toward something. To see what that something is, and the larger arrangement we are part of, we have to step outside the boundary of our own galaxy and into the neighborhood of galaxies that surrounds it. Step outside the Milky Way and look around. The nearest large galaxy is Andromeda, 2.5 million light-years away. A flat spiral disk much like our own, but slightly larger, containing perhaps 1 trillion stars to our own 200 billion or so. Andromeda is visible to the naked eye on a dark moonless night, a faint, elongated smudge in the constellation that bears its name. The light reaching your eyes from Andromeda left it 2.5 million years ago, when the earliest members of the human lineage were just beginning to walk upright on the plains of East Africa. The galaxy, as you see it tonight, is a snapshot of how it was when our ancestors were not yet our ancestors. Andromeda and the Milky Way are not alone. Between and around them, in a region perhaps 10 million light-years across, lies a small cluster of galaxies called the Local Group. There are about 80 members in the catalog, though most of them are small. 2 of them are dominant. Andromeda and the Milky Way together contain most of the mass of the entire group. After them comes the Triangulum Galaxy, a smaller spiral about 3 million light-years away, with perhaps 40 billion stars. The rest are dwarf galaxies, small irregular collections of a few million to a few 100 million stars, scattered around the 2 large spirals as gravitationally bound companions. Some of them orbit Andromeda, some orbit the Milky Way. Some drift on long elliptical paths that take them slowly through the gravitational field of both major galaxies. All of these galaxies are moving. Each one has its own velocity through space, set by where it sits in the gravitational landscape of the group, and by whatever motion it inherited from the larger cosmic flows long ago. The smaller galaxies orbit the large ones on paths that take billions of years to complete. The 2 large galaxies orbit each other very slowly in a long approach that has been going on since the universe was about half its current age. The 2 largest companions of the Milky Way are the Large and Small Magellanic Clouds, irregular galaxies visible from the southern hemisphere as 2 pale patches of light. They were named for Ferdinand Magellan's expedition of the 16th century, whose crews recorded them as a permanent feature of the southern sky, though they had been known to indigenous peoples of the southern hemisphere for as long as anyone had lived under those skies. The Large Magellanic Cloud lies about 160,000 light-years from us. The Small Magellanic Cloud lies about 200,000 light-years away. Both are gravitationally bound to the Milky Way and are slowly falling toward it. They are currently moving at about 320 kilometers per second, on long arcing paths that will eventually bring them into the main body of our galaxy. The Large Magellanic Cloud is leaving behind a long stream of gas and stars, called the Magellanic Stream, marking the path it has taken through the Milky Way's gravitational field over the past 2 billion years. The stream itself is a record of motion frozen into the gas. As the Magellanic Clouds have looped through their long orbits, the Milky Way's gravity has pulled material out of them and stretched it into a vast curving ribbon that wraps almost all the way around our galaxy. The ribbon is hundreds of thousands of light-years long, and it is visible in radio observations as cold hydrogen gas that has been dragged along, slowly, behind the two small galaxies. Every loop the Magellanic Clouds have made has contributed a section to the stream, and each section preserves the speed and direction the gas had when it was pulled away. It is the long exposure trace of two galaxies in motion, written in interstellar hydrogen across half the sky. The Milky Way also has at least 60 smaller dwarf galaxies in orbit around it, most of them faint enough that they have only been discovered in the past few decades using large surveys of the southern sky. They have names like Draco, Ursa Minor, Sculptor, and Fornax after the constellations in which they appear. They are small, only a few thousand to a few million stars each, and they orbit the Milky Way on long elliptical paths that take hundreds of millions of years to complete. Many of them have already been partially torn apart by tidal forces from the Milky Way's gravity, leaving long streams of stars trailing behind them as they orbit. The Sagittarius dwarf, in particular, is so badly disrupted that its remains now wrap around the entire Milky Way like a long loose ribbon, the slow disintegration of an entire galaxy spread out across the sky. The galaxies that have already been absorbed into the Milky Way are no longer visible as separate objects, but the stars they once contained still move through our galaxy on paths that betray their origin. Astronomers using the Gaia Space Telescope, launched by the European Space Agency in 2013, have been mapping the positions and motions of more than 1 billion stars in our galaxy, and have identified populations of stars that move together in distinctive patterns inherited from the galaxies they came from. The Gaia data has effectively let us excavate the past of the Milky Way, peeling apart the history of mergers and acquisitions that built our galaxy into the structure it is today. We can see, in the motions of individual stars, the traces of collisions that happened billions of years ago. The most striking feature of the local group, when one steps back and looks at the motions of its members, is the slow approach of Andromeda. The two large galaxies are moving toward each other at about 110 kilometers per second. The vast majority of galaxies in the universe are receding from us, carried apart by the expansion of space itself. Andromeda is one of the few that is approaching, because it is close enough that the gravitational attraction between the two galaxies overcomes the cosmic expansion of the space between them. The local group is one of the regions of the universe in which gravity is strong enough to hold a small collection of galaxies together against the general expansion. Inside the group, the galaxies follow their own gravitational dance. Outside it, the universe expands. The collision of Andromeda and the Milky Way is therefore not in doubt, only in timing. Current calculations, based on careful measurements of Andromeda's motion, suggest the first close approach will happen in about 4.5 billion years. The two galaxies will swing past each other for the first time, then loop back together, then settle into a final merger over the following billion years or so. The result will be a single large elliptical galaxy, sometimes called Milkometa in the popular literature, containing all the stars and gas of both original galaxies. The Triangulum galaxy will likely be drawn in as well, contributing its 40 billion stars to the merger. What this collision will look like, despite the dramatic phrasing, is not what most people imagine. Galaxies are mostly empty space. The stars within them are separated by enormous distances compared to their sizes. The nearest star to our Sun is about 4 light-years away, and the Sun itself is about a 4/millionth of a light-year across. The ratio of distance between stars to the size of the stars themselves is roughly the ratio of distance between grains of sand, if the grains were spread out across an entire country. When two galaxies collide, almost no stars actually hit each other. The gas clouds in the two galaxies do collide, producing waves of compression that trigger bursts of new star formation. But the stars themselves slide past one another with vast distances between them. From the perspective of any individual star, the collision would be felt only as a slow change in the gravitational landscape over hundreds of millions of years. as the structure of the local sky reshapes itself. There would be no impact, no destruction, no visible disturbance to any planet in orbit around any star. What there would be, eventually, is a different sky. After the merger, the night sky as seen from the Earth, if the Earth still existed and the sun still shone, would look entirely different. The Milky Way's familiar band across the sky would be replaced by a complex pattern of streams and arcs of stars, the disrupted remains of the two original disks, slowly settling into the spherical or ellipsoidal arrangement of a single new galaxy. The galactic center, currently in Sagittarius, would no longer be in the direction it now lies. The bright band of stars we know would be gone, replaced by something larger and more diffuse, perhaps not even recognizable as a galaxy from the inside, in the same way the Milky Way is recognizable to us now. For now, though, the Milky Way and Andromeda continue their slow approach. Andromeda's image hangs in our autumn sky as a faint patch of light, smaller than the full moon, in the corner of the constellation that bears its name. The light reaching us tonight left it 2.5 million years ago, and the galaxy itself is closer now, by an amount measurable but undetectable to any observer working with anything less than the most precise astronomical instruments. The two galaxies are caught in a slow gravitational embrace that began billions of years ago and will not complete for billions more. It is worth pausing on the slowness of all this. Andromeda is approaching us at 110 kilometers per second, which is to say nearly 400,000 kilometers per hour. That speed sounds large, and it is, by any standard of human experience. But the distance is so vast that even at this speed, the journey takes billions of years to complete. To cover a single light year, at 110 kilometers per second, requires nearly 3,000 years. Andromeda is 2.5 million light years away. The cosmic dance is real, but its rhythm is set by distances so large that the entire history of human civilization, from the first cities to today, has occupied a small enough span of time that Andromeda has moved only about 1/100th of 1% of its way toward us during it. The whole of recorded history is, on this scale, a small forward step in a journey that began long before anyone was watching and will continue long after the watchers are gone. The local group, as a single dynamical structure, is itself in motion. The combined mass of all the galaxies in the group is about 3 trillion solar masses, and this entire collection of objects is being pulled by larger structures in the universe beyond it. The same motion of the Milky Way that we have already discussed, the 600 kilometers per second drift in the direction of Leo, is shared, with small differences, by every galaxy in the local group. We are not alone in the fall. The whole group is being drawn towards something larger by a gravitational current that begins to reveal, as we follow it outward, the much larger architecture of the universe in which all of this is embedded. It is worth pausing on the picture this paints. Inside the local group, gravity has organized a small island of galaxies that hold together against the expansion of space. The galaxies within this island circulate around each other on long elliptical paths, the smaller ones orbiting the larger, the two large spirals approaching each other in a slow gravitational waltz that began billions of years ago. The island itself, this whole arrangement of 80 bound galaxies, drifts as a single object through the surrounding cosmos. From outside, the local group would appear as a compact gravitational unit, slightly elongated, populated by a few bright members and many faint ones, moving steadily through intergalactic space in a particular direction at a particular speed. We live inside one of these units. There are millions of others scattered through the visible universe, each one a similar gravitational island, each one with its own internal dance and its own motion through the larger cosmic current. The local neighborhood, in this sense, is a small region of gravitational coherence within a much larger flow. Inside the group, gravity has organized matter into a tight cluster of galaxies bound to one another. Outside the group, the universe is dominated by larger structures, by streams and walls and sheets of galaxies arranged in patterns that span hundreds of millions of light years. Our small island of about 80 galaxies sits within this larger architecture, drawn by its gravity, carried along on its motion. To understand where we are being pulled and what is doing the pulling, we have to step out further still, into the patterns that organize the universe, at scales millions of times larger than our own galaxy. For most of the 20th century, astronomers assumed that the motions of galaxies beyond our own neighborhood were dominated entirely by one thing. The general expansion of the universe was supposed to carry every galaxy outward from every other, at speeds proportional to distance, in a smooth and uniform recession. Any small deviations from this pattern were treated as the random peculiarities of individual systems, the local pulls of nearby clusters on the galaxies within them. The large-scale flow of the universe, beyond the scales at which gravity could organize a few galaxies into a bound group, was supposed to be featureless. This picture began to come apart in the 1970s and 80s, when astronomers became able to measure the motions of large samples of galaxies with enough precision to detect deviations from the smooth Hubble flow. What they found was that whole regions of the universe, containing thousands of galaxies, were moving together as great rivers, drifting in the same direction at the same speed through the surrounding cosmic landscape. The pattern was not random. The galaxies in our part of the universe, including the local group and a much larger collection of neighboring groups, were all falling toward a common point, somewhere in the direction of the constellation Centaurus. The work that established this was done by a group of 7 astronomers who became known in the literature as the 7 Samurai, working in the mid-1980s. They measured the distances and velocities of about 400 elliptical galaxies in our region of the universe, and they found that all of them, scattered across hundreds of millions of light years, were drifting toward a single direction in the sky at speeds of several hundred kilometers per second above what the smooth expansion of the universe would predict. The implication was clear. Something with an enormous gravitational pull was sitting somewhere in that direction, hidden behind the obscuring band of the Milky Way's own disk, drawing thousands of galaxies toward it across vast distances of intergalactic space. They called it the Great Attractor, and the name has stuck. The Great Attractor itself was difficult to identify because it lay in a part of the sky that is hard to observe. The disk of our own galaxy, full of stars and gas and dust, blocks much of the light from objects directly behind it, creating what astronomers call the zone of avoidance. The Great Attractor turned out to be sitting in this zone, hidden behind our own galaxy's disk, partially obscured by foreground stars and dust. Over the following decades, astronomers used X-ray and infrared observations, which penetrate the dust better than visible light, to identify what lay behind. The answer turned out to be a vast supercluster of galaxies, centered on a cluster called Norma, sitting about 250 million light-years from us. The Norma cluster contains hundreds of galaxies, and around it are arranged thousands more in a sprawling structure that contains, in total, the mass of perhaps 100,000 galaxies like our own. There is something quietly poetic about this. The largest gravitational structure pulling our galaxy through the cosmos sat for most of human history directly behind the stars our own galaxy made, hidden from view by the very disk that contains us. For thousands of years, astronomers looked up at the band of the Milky Way and saw it as a barrier across the sky, blocking the view of half the heavens beyond. The Great Attractor, which has been shaping the motion of our entire region of the universe since long before our galaxy formed, was on the far side of that barrier the whole time. We could not see it. We could only feel it in the cumulative motion it imposed on every galaxy in our part of the cosmos. We knew there had to be something there because of how the galaxies in our region were drifting. But to see what it was, we had to learn to look through our own galaxy with wavelengths of light our eyes were not built to detect. But even the Great Attractor was not the whole story. the motion of the galaxies in our region continued past the Great Attractor itself. As astronomers measured galaxies on the far side of the Norma supercluster, they found that those galaxies were also moving in the same direction. Whatever was pulling on us was pulling on regions further out as well, suggesting that the Great Attractor was a way station rather than a destination. Behind it, much further away, lay something even larger. That larger structure is called the Shapley supercluster, after the American astronomer Harlow Shapley, who first noted a concentration of galaxies in that direction in the 1930s without knowing what he was looking at. The Shapley supercluster sits about 650 million light-years from us, more than twice as far as the Great Attractor, and it is the most massive concentration of galaxies in the nearby universe. It contains around 100,000 individual galaxies arranged in a structure several hundred million light-years across. The gravity of this enormous concentration of matter is reaching across the intervening space and pulling thousands of intermediate galaxies, including our own local group, toward it at speeds of several hundred kilometers per second. The Milky Way's motion of 600 kilometers per second toward Leo, measured against the cosmic microwave background, is partly due to this pull. The Great Attractor contributes some of the pull. The Shapley supercluster contributes more. Other structures contribute smaller amounts. The total motion is the sum of all these gravitational influences, integrated over the entire history of the universe, expressing itself in the present moment as a steady drift in a particular direction at a particular speed. We are, in a strict and measurable sense, falling toward the Shapley supercluster, 650 million light-years away, at 600 kilometers per second. What this motion reveals, more than anything else, is that the universe is not smoothly populated. Galaxies are not scattered evenly through space. They are arranged in vast structures, in clusters and superclusters, and even larger arrangements, separated by enormous voids of nearly empty space. The mapping of these structures has been one of the major achievements of astronomy over the past 40 years. The Sloan Digital Sky Survey, which began operations in 2000, has measured the positions and distances of hundreds of millions of galaxies, and the resulting maps reveal a cosmic architecture that no one had anticipated when serious galaxy surveys began in the 1970s. The architecture has a name. It is called the cosmic web, and it looks like nothing so much as a vast, three-dimensional sponge or net. Galaxies are concentrated along thin filaments that stretch for hundreds of millions of light-years, with the densest knots at the intersections of filaments and the emptiest regions, called voids, lying in the spaces between. The voids are enormous. Some are more than 100 million light-years across, with hardly any galaxies in them at all. A spacecraft drifting through the middle of one of these voids would find itself surrounded by nothing for tens of millions of light-years in every direction, with even the nearest galaxies appearing as faint pinpoints lost in the dark. The filaments are crowded by comparison, dense with galaxy clusters and superclusters, all of them connected by streams of more diffuse matter and gas. The whole arrangement looks like a foam, or a tangled net, with the structure of matter strung along thin lines and sheets in a sparse three-dimensional pattern. This structure was not designed, it emerged. In the early universe, the matter was distributed almost uniformly, with only tiny irregularities in density from place to place. Over billions of years, gravity has slowly amplified those irregularities. Regions that started with slightly more matter attracted more matter, becoming denser. Regions that started with slightly less lost matter to their denser neighbors, becoming emptier. The pattern grew. Over the age of the universe, the small initial fluctuations have grown into the cosmic web we see today, with galaxies and clusters concentrated along the filaments and voids opening up in the regions between. The shapes of those filaments were ultimately determined by the patterns of dark matter, which makes up most of the gravitating mass in the universe, and which provides the gravitational scaffolding on which visible structures form. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii produced a map of the cosmic flows in our region of the universe, using measurements of galaxy motions to trace out the boundaries between regions that are flowing toward different destinations. The map revealed that the Milky Way and the local group lie at the edge of a vast structure that the team named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of about 100,000 galaxies, including the local group, the Virgo cluster, the Centaurus cluster, the Norma cluster, and many smaller groups, all flowing together toward the Great Attractor, and beyond it toward the Shapley supercluster. The boundaries of Laniakea are defined not by gravitational binding, but by the direction of motion of its members. Inside Laniakea, all the galaxies are flowing in the same general direction. Outside it, the flow turns toward different destinations. The Milky Way is part of Laniakea. The local group is a small island within it. The supercluster is some 500 million light-years across and contains 100 quadrillion solar masses of material in its galaxies and dark matter halos. Our galaxy occupies a small region near the outskirts of this larger arrangement, drifting along with its current, falling toward the gravitational center that organizes the whole. We have always been here, in this larger architecture. We did not know it was there until very recently, but the motions of our region of the universe have been shaped by it for billions of years. The map Tully's team produced was, in a sense, a portrait of our galactic address at the largest scale anyone had ever drawn. When you look at the map, the Milky Way appears as a tiny point near the edge of a vast, wing-shaped structure, with the Virgo cluster forming a brighter knot toward the center, and the Great Attractor lying near the gravitational floor of the whole arrangement. Lines of flow are drawn on the map, showing how galaxies in different parts of the region are drifting. And the lines all sweep inward, toward the deeper gravitational regions, like water flowing toward the lowest point in a landscape. Where the flow lines change direction is where one supercluster ends and the next begins. The boundaries of Laniakea, in this sense, are not walls. They are watershed lines, marking the divide between regions whose contents are flowing toward different destinations. We sit in this cosmic geography near the outer edge of our own watershed, drifting steadily down the slope toward the gravitational lowlands of our region. Beyond Laniakea, the picture continues to grow. Adjacent to our supercluster are others, with their own internal flows, their own gravitational centers, their own galactic populations. The Perseus-Pisces supercluster lies in one direction, the Coma supercluster in another. The huge Sloan Great Wall, a structure of galaxies more than 1 billion light-years long, has been mapped at the limits of current surveys. Each of these structures contains hundreds of thousands of galaxies arranged in flowing patterns of motion, each one drifting toward its own gravitational centers under the influence of its own local mass distribution. The cosmic web extends throughout the visible universe, with structures upon structures upon structures, all of them organized by gravity, all of them in motion. The largest of these structures are at the limits of what is reasonably called a single-bound object. At scales above a few hundred million light-years, the expansion of the universe overwhelms gravity, and structures cannot remain bound. The largest superclusters are not gravitationally bound in the strict sense. They are coherent regions of flow, places where galaxies are moving together in a particular direction, but they are not destined to collapse into single objects the way smaller groups and clusters eventually will. The cosmic web, at its largest scales, is a transient pattern, drifting and stretching as the universe expands around it. This brings us in the end to the question that has been hovering over everything we have discussed. The motions we have looked at, the rotation of the Earth, the orbits of the planets, the drift of the solar system around the galaxy, the dance of the local group, the fall toward the Shapley supercluster, all of these are motions that take place within the universe. They are motions of objects through space, organized by gravity acting on matter. But the universe itself, the geometry of space within which all these motions happen, is doing something stranger. Space itself is expanding, growing larger from moment to moment, carrying galaxies apart not by accelerating them through any medium, but by stretching the medium in which they sit. This expansion is the deepest layer of motion in the cosmos, the slow growth of the universe as a whole, and it deserves a closer look in its own right. For most of human history, the universe was assumed to be eternal and unchanging. The stars were thought to occupy fixed positions in a great celestial sphere. The same arrangement passed down from generation to generation across thousands of years. Aristotle, in the 4th century before the Common Era, articulated this view with particular clarity, dividing the cosmos into a changeable terrestrial realm beneath the moon and an unchangeable celestial realm above it. The view persisted in various forms for more than 2,000 years. Even Newton, in the late 17th century, assumed that the universe as a whole was static, infinite, and eternal, with the stars holding their positions through some kind of cosmic balance of gravitational pulls that he himself acknowledged he could not fully explain. The first serious challenge to this picture came not from observation, but from theory. When Einstein completed his general theory of relativity in 1915, he immediately applied it to the universe as a whole, and he found that the equations gave a surprising answer. A universe filled uniformly with matter could not be static. Gravity would pull the matter together, and unless something opposed the pull, the entire universe would collapse. Einstein, who shared the prevailing assumption that the universe must be eternal and unchanging, added a term to his equations called the cosmological constant, specifically designed to balance the gravitational collapse and produce a stable, static universe. He later called this addition the greatest blunder of his career, after the universe turned out to be doing something he had not anticipated at all. What the universe was actually doing was expanding. The first evidence came from the work of Vesto Slipher at the Lowell Observatory in Arizona, who in the 1910s and 20s measured the spectra of light from distant galaxies and found that almost all of them were shifted toward longer wavelengths, the red end of the spectrum. The shift was the Doppler effect, the same shift in pitch you hear when a passing ambulance recedes from you, applied to light from receding sources. The galaxies were moving away from us. Slipher did not know what to make of this. The galaxies themselves were not yet understood to be separate stellar systems comparable to our own, and the implications of the recession were not yet clear. The piece that connected the recession to a larger picture came from Edwin Hubble in 1929. Hubble, working with the 100-inch telescope at Mount Wilson Observatory in California, had spent the preceding years measuring the distances to nearby galaxies, using a particular type of variable star called a Cepheid variable, whose brightness varies in a predictable pattern that lets astronomers determine its distance. By combining his distance measurements with Slipher's recession velocities, Hubble found something extraordinary. The galaxies were not just receding, they were receding faster the further away they were. A galaxy twice as far away was moving away twice as fast. A galaxy 10 times as far away was moving away 10 times as fast. The relationship was linear and remarkably consistent across all the galaxies Hubble could measure. This is now called Hubble's law, and it has a simple but profound interpretation. If every galaxy is receding from every other galaxy, with the recession speed proportional to distance, the simplest explanation is that the universe itself is expanding. Imagine a balloon being slowly inflated, with dots painted on its surface. As the balloon grows, every dot moves away from every other dot. A dot twice as far from another dot moves away twice as fast, because there is twice as much rubber stretching between them. The motion is not actually motion of the dots through some pre-existing space. It is the stretching of the space the dots are sitting in. The galaxies in this picture are like the dots. They are not flying through the universe. The space between them is expanding, and they are being carried along. This idea had been anticipated theoretically. The Belgian priest and physicist Georges Lemaitre had derived solutions to Einstein's equations in 1927 that described an expanding universe 2 years before Hubble's measurements made the expansion observationally undeniable. The Russian mathematician Alexander Friedmann had derived similar solutions in 1922. Both men had recognized, on theoretical grounds alone, that the universe described by general relativity could be a universe whose geometry changed over time, and that an expanding universe was a natural solution to Einstein's equations once one stopped insisting on a static answer. When Hubble's observations came in, they confirmed what the theory had already suggested. The universe was expanding. The expansion is not motion of galaxies through space. This distinction matters. The galaxies are not flying outward through some pre-existing void at the speeds Hubble measured. The galaxies are essentially stationary in their own local neighborhoods, with whatever small peculiar motions they have inherited from gravitational interactions with their neighbors. The recession comes from the stretching of the space between them. Distant galaxies appear to recede at high speeds because there is a great deal of space between us and them, and all of that space is stretching at once. This also explains why the speeds inferred from Hubble's law can, for sufficiently distant galaxies, exceed the speed of light without violating any law of physics. The speed of light is the universal speed limit for objects moving through space. The expansion of space itself is not motion through space, and so it is not bound by that limit. Galaxies sufficiently far from us are receding faster than light, not because they are moving through space at superluminal speeds, but because the space between us and them is being added to, fast enough that the light they emit toward us cannot quite catch up to the growth of the distance. Beyond a certain distance called the cosmic event horizon, the expansion is fast enough that light from those regions will never reach us, even if it travels toward us for the entire future history of the universe. The implication that the universe is expanding led naturally to a further implication. If the universe is expanding now, it must have been smaller in the past. Running the expansion backward, the universe must have been progressively denser and hotter at earlier times, until eventually, at some finite time in the past, all the matter and energy in the universe must have been concentrated into a state of extreme density and temperature. This idea, the Big Bang, was developed by Lemaitre and others in the late 1920s and 30s, refined by George Gamow and his collaborators in the 1940s, and confirmed observationally in 1964 when the cosmic microwave background was discovered. The cosmic microwave background is the relic light from the early universe, when the universe was about 380,000 years old, and the first hot dense plasma had just cooled enough to become transparent to light. That light has been streaming through the universe ever since, stretched by the expansion to longer and longer wavelengths, until today it arrives at our microwave antennas as a faint, cold glow filling the sky in every direction with a temperature of about 2 7/10 degrees above absolute zero. The cosmic microwave background is the most direct evidence we have for the Big Bang and for the expansion of the universe. It is, in a strict sense, light from the early stages of the expansion itself, made visible to us by the same process that has been stretching it for nearly 14 billion years. The age of the universe, deduced from the rate of expansion and the patterns visible in the cosmic microwave background, is about 13.8 billion years. That is how long the universe has been expanding. Galaxies began to form about a few 100 million years after the Big Bang, condensing out of the cooling gas under the gravity of the dark matter that already filled space. Stars began to form within those galaxies, then planetary systems within those stars. Then, in at least one of those systems, the chemistry that eventually became life, and then minds capable of asking how it all began. The motions we have looked at, all of them, are products of this long expansion. The spinning planets, the orbiting moons, the wheeling galaxies, the drifting superclusters, all of them exist because the universe has been expanding long enough for matter to collect into the structures that move within it. The expansion is also not constant. The rate at which the universe is expanding has changed over its history, and the change has been one of the more surprising discoveries of modern cosmology. For most of the 20th century, astronomers assumed that the expansion was slowing down, gradually decelerated by the mutual gravitational pull of all the matter in the universe. The expansion had begun fast in the Big Bang, the reasoning went, and the gravity of the matter was working to bring it eventually to a halt, or possibly to reverse it into a contraction. The question of which outcome would prevail, eternal expansion or eventual recollapse, depended on the density of matter in the universe, and was the subject of decades of research. In 1998, two independent teams of astronomers announced that the expansion was not slowing down, it was accelerating. Both teams had been measuring the brightness of distant Type 1a supernovae, a particular class of stellar explosions whose intrinsic brightness is known with enough precision that they can be used as standard candles to measure cosmic distances. By comparing the observed brightnesses of distant supernovae with their measured redshifts, the teams could plot the history of the universe's expansion rate over the past several billion years. They expected to see the expansion slowing. What they saw instead was the expansion speeding up. The most distant supernovae they observed were fainter than they should have been if the expansion had been decelerating. They had to be further away than the simple expansion model predicted, which meant the universe must have spent the intervening time expanding faster than the model assumed. The expansion was accelerating. The acceleration is driven by something called dark energy, a name chosen for its modesty and its acknowledgement of ignorance. Dark energy is the term used for whatever is causing the expansion to speed up. It is, by current measurements, the dominant component of the universe, accounting for about 68% of the total energy density. Ordinary matter, the kind in stars and planets and people, accounts for less than 5%. Dark matter accounts for the remaining 27%. The bulk of the universe by energy content is something that none of our instruments can detect except through its effect on the expansion rate. And what it is remains one of the great unsolved problems in modern physics. The dark energy may, ironically, be something very close to Einstein's cosmological constant. The constant he added to his equations in 1917, then withdrew in embarrassment after Hubble's observations, may have been roughly correct after all. The universe really does contain a constant background energy density that produces a kind of cosmological repulsion, and it really does drive the universe toward eternal expansion. Einstein had the right form of the equation. He had only assumed the wrong value, one chosen to produce a static universe rather than an expanding one. What he called his greatest blunder may turn out to have been a closer approach to the truth than he realized. The acceleration of the expansion means that the universe is, in the long term, headed toward a peculiar fate. As the expansion continues to accelerate, the rate at which distant galaxies recede from us will grow. Eventually, perhaps 100 billion years from now, all galaxies outside our own local group will have receded so far and so fast that their light can no longer reach us. The local group, gravitationally bound and falling together against the expansion, will remain. Everything beyond it will fade from view, redshifted out of detectability, gone. Any observers in the distant future, looking out at their sky, will see only the merged Milky Way galaxy and its few faint companions. The rest of the universe will, from their perspective, simply not be visible at all. For now, though, the universe expands at a rate we can measure. Every cubic meter of space, somewhere in the universe, is growing by about 700 trillionths of a percent every year. This sounds vanishingly small, and over a single year, it is. But over the age of the universe, the cumulative expansion has carried the original infant cosmos out to the 93 billion light-years across that the observable universe now spans. The expansion continues. The galaxies continue to drift apart. The cosmic web continues to stretch. Every motion we have looked at, all the way down to the rotation of the Earth, takes place within this larger growing geometry and is shaped by it in ways small and subtle but real. The cosmos in motion, then, is not just a collection of moving objects. It is a moving geometry, growing and stretching as it carries everything within it. The motions of galaxies, of solar systems, of planets, of moons, of human bodies, are all happening inside a universe that is itself in motion at the deepest level. Nothing is at rest. Nothing has ever been at rest. The patterns we see are not the imposition of stillness on a moving world. They are the long, slow, beautiful continuations of motions that began long ago, and have, by the simple laws of physics, never stopped. Return to where this video began. Wherever you are sitting or standing, whatever room or street holds you right now, the motions are all in place. The ground beneath you is sweeping eastward at over 1,000 kilometers per hour as the planet spins. The planet itself is hurtling around the sun at 30 kilometers per second. The sun is carrying its family of worlds around the galaxy at 230 kilometers per second. The galaxy itself is drifting through the universe at 600 kilometers per second, falling toward distant superclusters that no one will ever reach. And the universe in which all of this is happening is itself expanding, stretching the geometry through which the galaxies drift, growing larger from moment to moment. None of this has stopped. None of it has ever stopped. None of it is going to stop. The cosmos in motion is not a metaphor. It is a literal description of where everything is and what it is doing. Every star in the sky tonight is on its own orbit, traveling at its own speed, set by where it sits in the gravitational landscape of the galaxy. Every galaxy beyond the sky is on its own larger trajectory, set by where it sits in the architecture of the cosmic web. Every planet, every moon, every asteroid, every comet, every grain of interstellar dust is moving on its own path, governed by the same simple laws of motion that govern any object in the universe. The whole vast intricate dance has been going on since long before there was anyone to watch it, and it will continue long after the last watcher is gone. And yet, when you look up at the night sky, none of this is visible. The sky looks still. The stars hold their familiar arrangements. The constellations our ancestors named thousands of years ago are essentially the same constellations we see today. The dome of the heavens has the same calm, unchanging quality it has had for the whole of human history. The motion is there. It is simply too slow, or too smooth, or too shared with our own, for our senses to register it. This is, in the end, what makes the cosmos look the way it does. Not stillness, but motion organized at scales too large and too gentle to perceive. The Earth turns smoothly, without bumps or jolts. The orbit around the sun is a continuous fall, with no sensation of falling. The galaxy rotates so slowly that the constellations do not change shape in a single human lifetime. The expansion of the universe is gentle enough that the galaxies we can see do not, from one year to the next, appear to move noticeably. The patterns of the night sky have been stable across the whole span of recorded history, and they will likely be stable for many human lifetimes more, even though every component of them is in continuous motion. Consider for a moment the ordinary experience of being a person in a room. The chair holds you up. The floor stays beneath your feet. The air sits still around you. The cup on the table does not slide. Everything in your immediate world behaves as though it were perfectly stationary, and you can go about your day in the comfortable assumption that nothing around you is moving in any way that matters. The assumption is, in the strictest physical sense, false. The chair, the floor, the air, the cup, your body, all of it is being carried along on the same vast journey, at the same speeds, in the same direction. The carrying is so uniform that nothing inside the room can detect it. There is no test you could perform, no measurement you could make using only objects inside the room that would tell you the planet is spinning, the orbit is moving, the galaxy is turning, the supercluster is falling. The room itself participates in all of these motions completely. Your senses, built for life inside such rooms, never encounter anything moving differently. So you experience stillness, and the experience is real, even though the underlying physical situation is not still at all. This is one of the most beautiful and least obvious things about the universe we inhabit. The motions that hold it together do not announce themselves. They do not produce wind or noise or visible disturbance. They are not the violent rushing motion of objects through space that human imagination tends to picture when it hears the word motion. They are smooth, steady, balanced motions, organized by gravity into stable patterns that endure for billions of years. The cosmos is in motion, not the way a storm is in motion, but the way a great river is in motion, flowing continuously at a pace too steady to feel. Newton's first law, the simple observation that things in motion tend to stay in motion, turns out to be the deepest physical principle behind all of this. Once any object is moving, it requires nothing to keep moving. Friction is what stops things, and most of the universe is empty enough that friction is essentially zero. So the motions, once started, continue. The Earth has been spinning for 4.5 billion years because nothing significant has slowed it down. The Sun has been orbiting the galactic center for the same length of time, for the same reason. The galaxies have been drifting apart for nearly 14 billion years because the expansion of space, once begun, simply continues. The cosmos stays in motion because that is what motion does in the absence of anything to stop it. Gravity organizes the motion. Without gravity, the universe would be a chaotic dispersal, with everything flying away from everything else in random directions. With gravity, the motion takes on structure. Particles collect into clouds. Clouds collapse into stars. Stars gather into galaxies. Galaxies group into clusters and superclusters. Each scale of organization is held together by gravity acting on motion, with the moving objects circling their gravitational centers in orbits that can last for billions of years. The patterns we see in the sky, the spiral arms of the Milky Way, the dance of Andromeda toward us, the fall of our supercluster toward Shapley, are all consequences of the interplay between motion and gravity, working continuously across the cosmos to produce structure rather than chaos. There is something quietly remarkable about the fact that the universe organizes itself this way. The principles involved are very simple. Newton's 3 laws of motion. Newton's law of gravity, refined by Einstein where the gravity becomes strong. The conservation of energy and angular momentum. The expansion of space itself. With just these elements, and the enormous time the universe has had to apply them, the cosmos has built itself into the layered structure we now see. Planets around stars, stars in galaxies, galaxies in groups, groups in superclusters, superclusters strung along the cosmic web. The architecture is real. The motions that built it are real. And neither one is finished. The universe continues to evolve, continues to expand, continues to organize itself, continues to move. For most of the history of life on Earth, none of this was known. Our ancestors looked up at the sky and saw the same patterns we see, but they had no way to know how the patterns came to be or what was happening within them. The stars seemed fixed because they did not visibly move. The sun seemed to circle a stationary Earth because that is what it appeared to do. The cosmos was assumed to be eternal and unchanging, with motions occurring only on the Earth and in the small region of space immediately above us. The discovery of how things actually are has taken several centuries of careful observation and theory, beginning with Copernicus and Galileo and Kepler and Newton, and continuing through Einstein and Hubble and Rubin and the generations who have since refined the picture. Each step has revealed more motion on larger scales, organized by simpler principles than the previous generation had imagined. The work that was required to learn it should not be passed over lightly. Telescopes had to be built and rebuilt across centuries. Spectrographs had to be invented and refined. Photographic plates had to give way to electronic detectors. Computers had to become capable of handling the enormous data sets that modern surveys produce. Generations of astronomers spent careers measuring the positions and motions of stars and galaxies, refining their methods, checking each other's work. The picture we now have was not handed down by any one person. It was built up grain by grain, observation by observation, by thousands of people across hundreds of years. The fact that an ordinary listener today can know that the local group is falling toward the Shapley supercluster, or that the Milky Way is 14% of the way to a collision with Andromeda, or that the Earth's rotation is slowing by milliseconds per century, is the product of an enormous collective human effort that began with people looking up at the same sky everyone has always looked up at, and asking what was actually going on. What stays with you once the picture is in place is a different sense of the world. The chair you are sitting in is hurtling through space at nearly 2 million kilometers per hour. The room you are in is part of a planet orbiting a star in the outer reaches of a galaxy that is one of trillions, all of them drifting through a universe that is itself in motion. The sun above your roof has been on a long curving journey for billions of years, and your body, every atom of it, is participating in that journey at this very moment. The stillness of the night sky is the appearance produced by all of this motion happening at once, smoothly, in balanced patterns that produce stable arrangements rather than chaos. The cosmos is not still. It has never been still. The stillness was always a feature of how we saw it, not of what it actually is. There is a particular kind of quiet wonder that comes from holding this picture in mind. It is not the wonder of the spectacular. The motions we have walked through are not violent. They are not loud. They do not flash in the sky or rumble through the air. They are continuous, patient, slow on human scales, and yet they hold together every structure in the universe and have been doing so since long before any of us existed. To know that this is what the universe is doing, beneath the apparent stillness of the night sky, is to have access to a fact about the world that is quietly enormous. The stars are not fixed. They are moving on their own paths, in their own time. The galaxy is rotating. The universe is expanding. The atoms in your body are participating, right now, in a vast cosmic motion that began in the early universe and has continued without pause ever since. The next time you stand outside on a clear night and look up at the sky, you can hold this in mind if you wish. The sky will still look still. The stars will still appear fixed in their familiar patterns. Nothing in your senses will tell you that you are spinning on a planet, orbiting a star, riding a galaxy, falling through a supercluster, drifting in an expanding universe. But all of that is true. It is happening. It has been happening since long before you arrived and will continue long after you are gone. The cosmos stays in motion not because anything pushes it, but because, once set in motion, that is what it does. Stillness is a perception. Motion is the underlying truth. In a sense, This is the simplest possible picture of what the universe is doing. There is matter. There is gravity. There is empty space across which matter can travel without resistance. Once these three things are in place, the rest follows. Matter pulls on matter. Matter falls toward matter in patterns shaped by where it started and how fast it was moving. The patterns produce orbits, rotations, drifts, and flows. Empty space, by being empty, lets the motions continue without ever slowing down. And the space itself, on the largest scales, stretches as the universe expands, carrying the motions outward with it. This is everything. There is no hidden machinery. There are no engines. There is nothing keeping it going except the simple fact that, in the absence of friction, motion does not stop on its own. The cosmos is in motion because it was set in motion long ago, and the laws of physics do not provide a way for it to be otherwise. If anything in this video has stayed with you, leave it a moment to settle before the next thing claims your attention. We will be back soon with another mystery from the sky.